In this final installment of my series, we approach the culmination of the scientific revolution, beginning with Galileo. You recall that we left off last time with Kepler and his three laws. As a follow-up to Kepler's work and as an introduction to Galileo, I want to tell you next about the first astronomer to use a telescope. While Kepler's discovery of his three laws provided compelling support for the heliocentric model, it was Galileo who drove the final nail in the coffin of the Ptolemaic model by making a simple but monumental direct observation. Galileo did not invent the telescope, but he was the first to make one good enough to look at the night sky and discover some of its secrets. One of his projects was to study Venus. If you study Venus over time, you will know that for periods of time Venus is a little bit east of the Sun, and we see it in the evening after the Sun has set. During other periods of time, Venus is a little bit west of the Sun, and we see it in the morning before the Sun has risen. At other times, Venus is so close to the Sun that we can't see it at all. Now, when you look at Venus with the naked eye, you probably wouldn't be able to tell that it goes through phases similar to the phases of the Moon. However, when Galileo first looked at Venus through a telescope, he might have seen this, a crescent shape. He would understand, of course, that what he was seeing was sunlight reflected off the surface of Venus. As this diagram shows, in the Ptolemaic model, Venus is always closer to Earth than the Sun, as they both orbit the Earth. During its epicycle, Venus is sometimes east of the Sun from our vantage point, and sometimes it is west of the Sun. However, in the Ptolemaic model, it would always appear less than half full. As Galileo studied Venus over months, he found in fact that sometimes Venus was a slim crescent, sometimes it was half full, and sometimes it was 3/4 full, or perhaps a bit more. This can only happen if Venus is revolving around the Sun, so that sometimes it is behind the Sun from our vantage point. From a scientific viewpoint, the Ptolemaic system was now dead and buried. Unfortunately for Galileo, the Catholic Church at the time considered his view to be heresy. He was sentenced to house arrest for the remainder of his life, and his books were banned. Many, including Einstein, have called Galileo the father of modern science. He didn't exactly invent the scientific method, but he did perhaps more than anyone else before him to demonstrate its power. Like Copernicus, he believed that nature is essentially mathematical in its structure. He famously said, "Mathematics is the language in which God has written the universe." Now, having convinced himself that the geocentric model was wrong, Galileo realized nevertheless that much of the resistance to the heliocentric model in others was rooted in people's common perception that the Earth is not moving. Surely, according to common sense, we would feel the motion if the Earth was revolving around the Sun. But common sense is sometimes wrong, so Galileo did a thought experiment to convince himself, and perhaps others, that our common sense was misleading.
If, like a galloping horse, the Earth is moving through space at great speeds, why can't we feel the movement? Galileo thought it was possible that the Earth could spin on its axis fast enough to cause night and day without anyone being able to feel the motion.
What is really exciting about Galileo, and you see it exactly the same in Einstein too, was the way he picked up what seemed to be an absolute impossibility. He said, we have this incredibly strong evidence that the Earth is not moving. Everything that our senses tell us is that the Earth is not moving. And yet Copernicus has got these rather strong arguments from astronomy to suggest that the Earth is moving. So then Galileo says, well, this actually should tell us something very deep about how nature works.
In Galileo's thought experiment, a horse represented the motion of the Earth. If the rider dropped a ball while the horse was standing still, the ball would, just as one might predict, fall straight down, landing beside the horse. But, Galileo thought, what would happen if the ball was dropped while the horse was moving through space in a gallop? Would the ball now fall behind the moving horse? No, thought Galileo, for in his thought experiment, the forward motion of the horse would be translated through the rider's hand to the ball, so that when the ball was dropped, it too would continue to move forward, landing beside the horse just as before. He thought when the horse and the ball shared the same forward motion, it appeared as if the motion didn't exist. So, Galileo reasoned, it is possible that, like the ball and the horse, we are sharing the motion of the earth without being able to feel it.
There is a sort of a principle of relativity where if you're sort of moving with the earth, everything shares the same motion. Not only is the earth moving, but I'm sharing that motion as well. And therefore it is all hidden. It was probably the first really great thought experiment in physics. In fact, he was so confident of the result, he never bothered to do the experiment to show it was right.
Here's an updated version of Galileo's thought experiment. The trolley is moving to the right at a constant velocity. The boy throws a ball up in the air. There are two observers. Do you see what's going on? The formal concept of vectors had not yet been invented, but Galileo clearly thought in terms of vector quantities. Let's break this down. First, let's focus on observer A. If he were in an enclosed boxcar with no windows, he would have no way of knowing from any immediate evidence that he was moving to the right at any particular constant velocity. According to him, the ball goes straight up and down. There is no experiment he could do within the enclosed space to determine that he was moving. Of course, the boy is moving relative to observer B, and she does not see the ball go straight up and down. She sees it travel along this parabolic trajectory. The ball's initial velocity vector, that is, its initial speed and direction, according to B, can be found by adding vectors. To add vectors, we are allowed to move them around in vector space. Vector space is not a physical space. It's a conceptual space represented in a diagram. It's easy. Here you go. The purple vector represents the ball's initial velocity according to the girl observer. In other words, there is no such thing as absolute motion of constant velocity. All such motion is measured relative to some inertial reference frame. An inertial reference frame is a reference frame that is itself not accelerating. Otherwise, the choice of a particular reference frame is totally arbitrary. This is Galilean relativity. As an aside, Einstein will take Galilean relativity as a starting point and make one simple tweak, proposing that the speed of light will always be observed to be the same regardless of the reference frame, and his theory of special relativity will be born. But of greater relevance to our story here is the fact that Newton will make brilliant use of the concept of vector addition to prove Kepler's laws. Now, when you think of Galileo the scientist, you probably picture him dropping balls of different weights off of the Leaning Tower of Pisa. It's not clear if Galileo himself actually did this experiment, but similar experiments were being done, and Galileo was aware of the results. Although air resistance is a complicating factor, there are ways to minimize its effect. In any case, the results seem to confirm the following. Two balls of different mass and different weight will fall at the same rate. This finding contradicted the teachings of Aristotle. Now you might say, so what? Well, this was a big deal because up until the time of the scientific revolution, Aristotle was generally considered to be the authority on everything. Now scientists were willing and eager to question that authority. But there's still more to the story. Galileo knew about air resistance, and more generally, he knew about friction. For a variety of reasons, he realized that dropping things off of a tall building was not a good way to conduct precise experiments. So he decided to study balls rolling down ramps. He starts building these ramps. He makes them very smooth and he sets them up on marble floors so as to reduce friction as much as he can. Now, I can't tell you exactly how he proceeded with his investigations, but I have a pretty good idea, generally speaking, from what I read. So the specifics of the experiments that follow are hypothetical, but the results that we get will allow us to draw the same conclusions that Galileo drew. He designs his own water clock, one that would be more accurate than anything else available at the time. He starts a ball rolling down the ramp. The first thing he wants to figure out is the final velocity as the ball leaves the ramp. He has a meter stick and a water clock. What does he do? He measures out a distance d and he measures the time it takes for the ball to travel that distance. By definition, velocity times time equals distance. Of course, this equation is only valid if the velocity has remained constant over this distance. With a little ingenuity, Galileo convinces himself that he has successfully reduced friction enough so that the velocity remains very close to constant. From this, he concludes that any object will retain the same velocity indefinitely unless friction or other disturbing force acts upon it. This will eventually become Newton's first law, the law of inertia. What he really wants to find out is what's going on while the ball is rolling down the ramp. He measures out 5 meters and lets the ball go. He measures the time it takes to get to the bottom of the ramp, and it's 1.7 seconds. And he measures the final velocity as he has done before, and it is 6 meters per second. Side note, as much as possible, I decided not to clutter up my slides with units. You can assume that all units are in terms of meters and seconds. Now he increases the distance d shown here to 10 meters. What do you think the final velocity will be? It's 8.5 meters per second. Still not clear what's going on here. Galileo decides with a bigger ramp he could collect some more data. So here is a table of Galileo's data. It looks like the final velocity is related somehow to distance down the ramp and also to time on the ramp, but the relationship is not immediately clear. Now, if mathematics is the language of science, there are different ways of expressing that language. As we shall see, Galileo recorded his findings in terms of diagrams and very careful wording. However, we are going to translate those findings into the language of Descartes. Descartes came along a couple of decades or so after Galileo. Among many other accomplishments, Descartes invented the Cartesian coordinate system. And you can't talk about the origins of calculus without giving credit to Descartes for his contributions. So, with the help of Descartes, let's take Galileo's data and plot final velocity versus time. This looks promising. In fact, we can draw a straight line that fits the data pretty well. It looks like the final velocity equals the slope, m, which is a constant, times t, time. We can calculate the slope. It's the final velocity divided by t, and it turns out to be 3.6. That's the acceleration. And Galileo showed that for a ramp of any given slope, the acceleration down that ramp is a constant, regardless of how heavy the ball is. Acceleration is measured in meters per second, so that when you multiply it by the time in seconds, you get the correct units for the final velocity. Now that we see how velocity relates to time, let's see how distance traveled relates to time. If velocity is constant, the formula is simple. But here the velocity is changing from 0 to the final velocity. There must be some value for velocity, let's call it the average velocity, for which this formula would be correct. It must lie somewhere between 0 and the final velocity. Your intuition has probably already suggested that the average velocity is 1/2 the final velocity, and it turns out that your intuition is correct. And so the equation for d as a function of t is shown here. Of course, Galileo wants to construct a convincing mathematical argument supporting these relationships. Let me show you a diagram from one of his published works. Does this look familiar? If I label it for you, you can see how Galileo anticipated Descartes. We can divide the horizontal axis into equal increments of time and indicate the corresponding velocities along the vertical axis. Galileo understands that the slope of line segment PA is the acceleration. And we can rewrite this relationship as a more general formula. V sub n equals A times T sub n. More importantly, what Galileo is trying to show in this diagram is that the distance traveled between t sub 0 and t sub 3 is the sum of the areas of these rectangles, which, he is arguing, is the same as the area of triangle POA. Let me try to help you see that. The area of triangle POA is 1/2 base times height, or, in other words, D equals 1/2 times V sub 3 times T sub 3. More generally, we can say that for any time interval T sub n, the distance traveled is 1/2 times V sub n times T sub n. But wait, we already know that V sub n equals A, the acceleration, times T sub n. So, making the substitution, we get D equals 1/2 times A times T sub n times T sub n. Or D equals 1/2 times A times the square of T sub n. This relationship was the crowning achievement of Galileo's ramp experiments. Finally, we come to Sir Isaac Newton. Let's talk about Newton's laws and how they differ from Kepler's laws. Kepler's laws are descriptive laws or empiric laws. They merely describe recurring patterns based on observations of 5 planets orbiting a star. On the other hand, Newton's laws are intended to represent fundamental laws of nature. They are proposed to be true everywhere and for all time. We begin with the first of Newton's three laws of motion. In agreement with Galileo's work, Newton's first law states that a body moving with a constant velocity, including a velocity of 0, will continue with that same velocity unless a force acts upon it. Next, we have force equals mass times acceleration. Let's unpack this law with a simple example. Force is the cause of the motion, and acceleration is the result. In a sense, mass here is a measure of resistance to acceleration. So, for a given force, an increase in mass will result in a decrease in acceleration. In other words, we can rewrite the equation like this. Acceleration is equal to force divided by mass. So we can easily recognize that acceleration will be greater the greater the force or the smaller the mass, and vice versa. Furthermore, if two bodies are accelerating at the same rate and one has greater mass, then the force must be greater, and vice versa. Now recall where we saw that acceleration is constant. The larger ball has more mass, so its resistance to acceleration is greater. However, since it accelerates at the same rate as the smaller ball, the force of gravity acting upon it must be more by the same proportion. Therefore, the force of gravity acting on an object must be proportional to the mass of the object. In other words, the mass of an object is both a measure of its resistance to acceleration and also a measure of at least one factor contributing to the force of gravity acting upon it. On a side note, this is either an amazing coincidence or else it says something very profound about what mass actually is at the most fundamental level. Now, shortly before Newton entered the discussion, a scientist named Robert Hooke proposed that all celestial bodies possess a mutual attraction for each other. In other words, this attractive force was reciprocated. Then Newton comes along and makes two original contributions. First, he assumes that this attractive force is the same gravitational force that we observe on Earth between falling objects and the Earth itself. Second, this gravitational force is proposed to be reciprocal, and since it has been shown on Earth to be proportional to the mass of the smaller body, it makes sense to suppose that it is also proportional to the mass of the larger body. So now we get that the force of gravity between two bodies is proportional to the product of their masses. The final crucial step in developing this famous formula was making it an inverse square law. That is, the gravitational force is inversely proportional to the square of the distance between the two bodies. One source claims that leading up to the time of Newton, this inverse square law had been proposed by several other people for differing reasons. In any case, we can understand the logic of it in the following way. We adopt the concept of a gravitational field around a massive body like the Sun and represent it with field lines pointing towards the Sun. The number of field lines, n, is proportional to the mass of the Sun. In this model, a planet located anywhere on this green sphere will experience a gravitational force proportional to the density of field lines running through the sphere's surface. that density will be inversely proportional to the surface area of the sphere. And geometry has taught us that the surface area of a sphere is directly proportional to the square of its radius. So now we can add Newton's universal law of gravity to his list of laws. And it provides an easy way of understanding Newton's third law of motion, which is that for every action there is an equal and opposite reaction. I think this law is a little easier to understand if you simply substitute the word force for action and reaction. As we saw earlier, the force of gravity between two bodies acts upon them mutually. And in the case of the water skier, we can see that while the boat is pulling the skier is in fact exerting an opposite force on the boat, which is carried in the tension in the rope. Have you ever heard the expression, "the proof is in the pudding"? It is actually a contraction of an expression that dates back many centuries. The original form is much clearer in its meaning. The proof of the pudding is in the eating. Newton's laws of motion and his universal law of gravity are all well and good, but for any scientific theory to be of consequence, it has to prove its value by providing a deeper understanding of prior observations or by correctly predicting future observations. In the case of Newton's laws, the proof of the pudding was in the fact that Newton was able to use these fundamental laws along with mathematics and brilliant reasoning to derive Kepler's empiric laws. This is now known as solving the Kepler problem. Now, if you look up current approaches to solving the Kepler problem, you will find solutions that almost exclusively involve the lengthy manipulation of abstract equations using the methods of calculus, like this one here. However, even though Newton invented calculus, traces of calculus are hard to find in his magnum opus, the Principia, where he solves the Kepler problem. Instead, Newton tried to state his arguments in a more traditional and intuitive format, involving geometry, trigonometry, vectors, and deductive logic. That said, Newton does introduce the concept of infinitesimals in his solution to the Kepler problem, and that's where one can get a glimpse of how the principles underlying calculus are helping to shape his thinking. If you're curious to know exactly how Newton did it, you could read his Principia, but I wouldn't recommend it, certainly not in the original Latin. Most modern readers are going to find Newton's style and terminology so unfamiliar as to render the work incomprehensible. As an alternative, you could take a look at my website, where with the help of a book written by a Caltech physicist, I present a derivation of Kepler's three laws that I think is faithful to Newton's approach. You don't need any background in calculus, just some familiarity with vectors, geometry, and trigonometry.